Good morning, students. My name is Dr. T. Vamshi Prasad. I am working as a assistant professor in BVRIT Narsapur. Today, I will discuss about the applied physics course in dielectric material. So, today we can discuss about the what is the importance of dielectric material in engineering stream application and what are the properties of dielectric material, what are the applications, how it is useful for real life related to the uh, dielectric material and also for solid components. My lecture is introduction about the dielectrics and properties of the dielectrics and what is the differences between the polar and non-polar dielectric materials. Especially in dielectric material, the fundamental is the very important role in the applied physics. So, in this fundamental definition are related to the what is the dielectric constant, what is the dielectric permittivity, and what is the its polarizability. So, what is the relationship between the dielectric polarization, dielectric permittivity, and electric displacement vector? Related to the dielectric function, we can discuss about the types of polarization. The types of polarization is related to the polarizability content like ionic polarization, electronic polarization, orientation polarization, space charge polarization. In these types of polarization, the total polarizability can be calculated related to the ionic, electronic, space charge polarization and orientation polarization. So types of polarization is also the important for the dielectric material. Based on the types of polarization, we can find out about the internal field of a dielectric material in an atomic view, that is said to be Lorentz field. Based on the Lorentz field, we can also find out about the Clausius-Mosotty relation. This Clausius-Mosotty relation also explain about the relationship between the polarizability and dielectric permittivity and also about the ferroelectricity. The ferroelectricity is one of the application for the dielectric material. So we can discuss one by one related to the dielectric chapter. Now you can see here the introduction about the dielectric is generally dielectrics are non-conducting or insulating materials with large energy band gap. Okay, so especially in dielectric material, the energy gap become very wide so that the electrons cannot jump from the valency band to the conduction band in energy level diagram. In insulator, the valency electrons are very tightly bound to the parent atom. Okay, so that in insulator or dielectric material, the examples are mica, glass, wood, and Teflon. So it is said to be non-conducting material, like insulating material. Okay, even even with normal voltage or high thermal energy, the electrons are not released. That means it is they are pure conductors of electricity. When such material is kept under the external electric field, the polarization will take place. Polarization is one of the important key aspects for the dielectric material. Due to the pure conductor, dielectric material which possesses bound charges by its configuration. So, based on the bound charges, we are having for n number of atoms and molecules. That means in dielectric material, charges are having for different orientation like positive charges and negative charges. I am taking for one positive charge and one negative charge separated by some amount of distance d. That configuration is said to be dipole. Okay, so dipole is very important in the dielectric material. Based on electric dipole moment, the materials can be classified into the different categories. So here dielectric material which possesses bound charges by its configuration based on electric dipole moment, the materials can be divided into the polar content and non-polar content. So I am taking here electric dipole. Okay, electric dipole is composed of two opposite charges of equal magnitude. Equal magnitude means I am taking for one positive charge and one negative charge separated by some amount of distance r or d. Okay, it is said to be electric dipole moment. Due to bound charges, they constitute an electric dipole moment. It is very important for the dielectric material. First, the dipole is formed. After that, due to the bound charges, they constitute an electric dipole moment. So I am taking here one positive charge, one negative charge separated by some amount of distance. It is r. Okay. So I am writing dipole momentum P equal to Q into R. So polarization is equal to dipole moment per unit value. Okay. First of all, polarization is important. The polarization means when such material is kept in dielectric material under the external electric field, the polarization will take place. So the unit of dipole momentum is debye. It is a microscopic quantity. That means the interaction of electrical energy with matter is determined by the electromagnetic properties of the material. That is very important in the dielectric unit. I am repeating one more time. The interaction of electrical energy with matter is determined by the electromagnetic properties of the material. So it is the microscopic quantity. Coming to the next slide, under the influence of external field, the positive and negative charges are displaced from their equilibrium position and from the dipole, which are responsible for dielectric behavior of this material. Okay, so based on the behavior, the characterization of dielectric material mainly depends upon the frequency and temperature. Okay, here on a microscopic scale, under the steady state condition, these properties are conventionally described by the permittivity and permeability of free space. The point is here, on a microscopic scale, under the steady state condition, these properties are conventionally described by the permittivity and permeability of the material. So the characterization of dielectric material involves the frequency as a function of temperature or as a function of temperature at a given frequency. So here the measurement of dielectric properties involves the characterization of conduction mechanism, interfacial polarization, relaxation time, and also about the molecular interaction between the one atom to the another atom. That's why dielectrics are non-metallic materials. For the measurement of dielectric properties can be calculated in the solid component, liquid component and gaseous component. So here dielectrics are non-metallic material. It is having for high specific resistance and have the negative temperature coefficient of resistance. Okay, very important in dielectric unit. Dielectrics are negative temperature coefficient of resistance. For example, in semiconductor is a negative temperature coefficient of resistance. Conductor is a positive temperature coefficient. Related to the band theory of solids, the band theory of solids is able to explain about the behavior of metal as well as non-metal. We are taking about the non-metallic material, that is purely related to the insulating material. So there is a slight difference in the dielectric and insulator. Okay, especially the main function of dielectric is it is stores the electrical energy. For example, if you take for capacitor, it is the energy storage device. So like that, dielectric means it stores the electrical energy, while the function of insulator is to construct about the flow of current. That is about the main point here. Coming to the next slide, what are the properties of the good dielectric material? First of all, it should have the high resistivity to reduce about the leakage current. Very important point. It should have the high resistivity to reduce about the leakage current. Depends upon the dielectric material. Especially dielectric material having the high dielectric strength. The material should be having for high dielectric strength and also about the high mechanical strength because of the preparation of the dielectric material. It should have the high resistance. It should have the low thermal expansion. It should have the high thermal conductivity. It should have the low dielectric loss. It should have the low water absorption quality. Now you can see here dielectric material having for low dielectric loss. Especially in dielectric material, the dielectric loss will be compulsory, it is there. For the measurement of the liquid dielectric material, we are calculating about the what is the its dipole moment, what is the its relaxation time, how the relaxation time is useful for the excessive parameters like uh, inverse relaxation time and also about the molecular interaction between the polar material. So dielectric loss means we are in terms of mathematical expression, we are writing the equation as complex dielectric permittivity is equal to real part minus imaginary part. Sorry, you have to write here equation is this one, or this is for the real part and this is for the imaginary part. So this is the dielectric loss, E double prime. Okay, this is the real part. One is the storage of energy, one for the loss of energy. E dash is storage of energy, E double dash is loss of energy. So we can calculate about the loss of the dielectric material due to the any content material like solid material and liquid material. For the measurement of the liquid material, the dielectric loss is very high due to the absorption factor. Okay, coming to the next slide, what are the types of dielectric material? Okay, for the measurement of dielectric material can be calculated in different ways. For example, solid dielectrics is most commonly used like glass, rubber and mica. Okay, so dielectric materials having the insulating material. Teflon is also one of the example for dielectric material. Coming to the liquid dielectric material, alcohol is one of the example, and also for water is also one of the good example for liquid dielectric material, and also about the uh, uh, kerosene. Okay, kerosene also the dielectric material, but especially for dielectric material, we are calculating most of the time polar content material only. I will tell you what is difference between the polar and non-polar material. I also about the dielectric material, but we can say it is the non-polar dielectric material. Okay, I will explain what is the about the polar and non-polar material. So in liquid dielectric material, we can say oil, transformer oil, like cable oil, capacitor oil, vegetable oil can be used. So here oil is the important factor, liquid dielectric measurement. For the measurement of dielectric properties, we are taking about the cable. See, for example, cable. In the cable, we are using about the coaxial probe cable. Okay, coaxial probe measure means it is having for the reflection quotient will be more in the coaxial cable. Okay, for simple example, when an electromagnetic wave is passing through the cable, some part of the ray is transmitted and some part of the ray reflected. Okay, transmitted, and this is incident, this is reflected, remaining is transmitted. Okay, when an electromagnetic wave is sorry when an electromagnetic wave is passing through the dielectric material, so some ray is reflected and remaining is transmitted. So here the reflection quotient is very important for the dielectric material. For the reflection only, we can calculate about the impedance of the device. For the application point of view, impedance is important for dielectric waveform. Like if you go for the gaseous dielectric material, it can be used both for the insulator, also for cooling agent. It is different material. Okay, for the research point of view, dielectric material is applicable in the solid form and liquid dielectric material. Okay, coming to the gaseous dielectric, we are taking for air, hydrogen, nitrogen, helium, sulfur dioxide, propane. Okay, sanitizer is also one of the good example for liquid dielectric material. In corona time, everyone using about the sanitizer. It is also for the liquid content material. Okay, so high vacuum can also be used for dielectric material. Okay, so these are about the different type of dielectric material. Compared to the these three dielectric material, liquid dielectric is suitable for the measurement of the dielectric material. Okay, coming to the next slide. What are the applications of dielectric material? The application is the real life process, especially in dielectric material we are using for the metallic insulating material. For example, you can see here I am taking for different types of dielectric material like low dielectric constant, high dielectric constant. So what is the difference between the low dielectric constant and high dielectric constant is we are calculating here the permittivity of the dielectric material. The permittivity is, this is about the symbol permittivity. The importance of this notation is on a microscopic scale under the steady state condition, this property is conventionally described by the dielectric permittivity of the sample. Okay, so it is the permittivity related to the dielectric material. If you go for magnetic material, we are using about the mu. This is for the permeability of the material. Both are having the same characteristic. This symbol is applicable for dielectric material. This symbol is applicable for magnetic material. Permittivity and permeability. Okay. So coming to the application point of view, dielectric material having the larger application in field of engineering, medicine, industry and research. I am taking about the low dielectric constant material. It is used for the engineering, microelectronic, industry, computers and medical equipment. If you go for the high dielectric constant material, it is using for the semiconducting manufacturing process in which silicon dioxide. Here the sample preparation is taking for silicon dioxide is not suitable but widely used in microchip, integrated circuit like ICs, transistor like bipolar junction transistor and also for microprocessor and computers. The best example for dielectric material is oven. In every home, the microwave is there. So here, application point of view, what is the importance of the microwave in the dielectric material? So you can see the diagram. What is the principle involved in the microwave heating? See here, I am taking about the two different mechanism. One for the conventional heating, one for the microwave oven. The conventional heating requires about the every time you are using about the metallic vessels. It is the long time to cook the material. If you go for the microwave cooking, the time duration is very less. Especially in the microwave oven, we are using about the ceramic content material like ceramic content, glass material, paper plates. In this one you are using. So what is the principle involving in the microwave heating is, here especially for micro oven, the source is magneton. Okay, the source is magneton. Its power is nearly 400. Its power is nearly 400 watts to 1200 watts. Micro oven power. The source is a magneton. Magneton. The source is the magneton. The principle behind the micro oven is, when an electromagnetic wave of frequency, I am taking one particular frequency, that is 2.45 gigahertz. When an electromagnetic wave of frequency 2.45 gigahertz is passing through the polar material, which is water molecule. The polar material best example is water molecule. So here the water dipoles are try to rotate from one equilibrium position to the another equilibrium position. So what happens here? The rotational frequency of the water molecule, which is equal to the incoming frequency of the electromagnetic wave. Once again, I am repeating the point. The rotational frequency of the water molecule, which is equal to the incoming frequency of the electromagnetic wave. Generally, what happens here? The rotational frequency of the molecule, that means there are n number of dipoles in the material. There is a friction in the material. That friction is responsible for dielectric heating. That means the energy is released in the form of the heat. So the principle of micro oven is dielectric heating only. Very, very important point. It is for the dielectric material. In the oven, this is about the glass material. Okay, the top one is glass enclosed material. Here, any radiation to coming inside to the outside, it blocks about the radiation from inside to the outside. So every time we are keeping only the polar content material only in the oven. For example, if you keep about the non-polar content in the oven, the material does not get heated. Okay, why become the material does not have the dipole? Simple example, take 1 cup of water and 1 cup of oil, keep it in micro oven, set the timer 5 minutes. After the 5 minutes, open the glass door, you can observe which material is heated first. My answer is water content is heated first. That means water molecule will be heated first, oil content will not be heated. Oil content is purely for non-polar material. The water content is a polar content, polar material. So water molecule having about the permanent dipole moment, non-polar molecule having the zero dipole moment. That is about the difference. So in the oven, only three operators are there. Every time we are using one for the ceramic, glass material, and paper plates. The material is heated quickly. It is the less time process. If you go for conventional cooking, it is very about the longer time process. We have to add for external heating also. Okay. So which one is better means, my point of view, conventional cooking is the larger time. It takes about the 1 hour time or half an hour time. Micro cooking is a very less time to prepare about the food. Okay, that's why we are using about the micro oven. See, this is about the magneton. This is the source of the micro oven. The power socket will be there. This is about the glass door, stirrer, cooking cavity, turnitin. Okay, waveguide. Waveguide means this is about the electromagnetic wave. Its power is nearly 400 watts to 1200 watts. Okay, that is so. My point is, it is purely related to the insulating material, non-conducting material. Okay, application. So in this diagram, we are using for the circuit, like integrated circuit. Okay, so like coming to the various types of dipole moment. Dipole momentum is equal magnitude of positive charge and negative charge separated by some amount of distance. It is said to be dipole. In this one, permanent dipole is there, induced dipole momentum is there, temporary dipole momentum is there. Permanent dipole momentum is fully related to the polar dielectric material. That means molecular structure will have net dipole momentum with respect to origin and non-centrosemic. With the help of the permanent dipole moment, we can calculate about the molecular interaction between the alcohols, aldehydes, and amine and alcohols, like liquid A plus liquid B plus liquid C. Liquid A is water, liquid B is alcohol. That means the dipole moment is there or not. If it is dipole moment, what is the next step? That's why we are taking for permanent dipole moment. If you go for induced dipole moment is caused by the displacement of unlike charges by applying the electric field. The mesh method is about the parallel plate capacitor. The capacitor is the energy storage device. So induced dipole momentum is taking place. Induced dipole momentum is, the symbol is mu. This is said to be induced dipole moment. Temporary dipole moment, especially in dielectric atomic cube, we are having for atoms and molecules exhibit about the temporary dipole momentum related to the dispersion in the frequency range. Okay. See here, especially for dielectric material, we are having for a lot of confusion how the material is identified by the polar and non-polar material. Okay, so material which have ability to transfer electric effect without conducting. I am taking here dielectric exists basically in two different methods, one for the polar molecule, another for the non-polar molecule. Otherwise, we can say the polar dielectrics and non-polar dielectrics. So, what is the difference between the polar and non-polar? Polar dielectrics or polar molecules. That means polar molecule which possesses bound polar molecule which possesses asymmetric charge distribution. It is having for permanent dipole moment. I am saying here the structure is different. It is for asymmetric charge distribution. So here polar dielectrics are those in which the possibility of center coincidence of the positive as well as negative charge is almost zero. That means the center of gravity of positive and center of gravity of negative. The center of positive charge and center of negative charge do not coincide. That means almost zero with each other. See here, exam point of view, I am taking for H2, that is water, alcohols, proteins, and also for quartz material. These are purely related to the polar content only. If you go, I am choosing for water content. Water molecules having for permanent dipole moment. Just like in the previous slide, we are taking about the micro oven. We are keeping the 1 cup of water in the oven. The water content will be heated first. It is the dielectric heating. So the material is heated or not. If it is heating, what is the structure? It is the asymmetrical structure. There are asymmetrical shape. Some of the examples of polar dielectric is NH3, HCl and water. Like in this diagram, study of molecular interaction between the alcohols like OH, CO, like alcohols, aldehydes and amines. So here, why liquid is the most important factor for dielectric material? Liquid is the least understood state of water. Liquid is the least understood state of the dielectric material. So here hydrogen bonding is completely forming in the liquid material. Study of molecular interaction between the dielectric materials related to the biological sample and semi-solid material. In this diagram, OH is there, CO is there, and also for CH3 is there. The structure is different here. That means beta structure, it is for protein. Two strands are held together by forming about the hydrogen bond. To go for the non-polar material, in non-polar material, the material which possesses symmetrical structure and having about the zero dipole moment. What happens means in case of non-polar dielectric, the center of both positive as well as negative charges coincide. We can see here non-polar dielectric. In the absence of external electric field, the positive and negative charges are coincide. If you apply the external electric field, the charges are displaced. Positive charge is one direction, negative charge is another direction. So what is the example for non-polar dielectric is methane, benzene, CO2, CH4, methane. So here the positive and negative charges coincide. Dipole momentum of each molecule is non-polar system is zero. It is the symmetrical structure. Like it is the symmetrical structure. So the dipole momentum is zero. If we keep non-polar content in the oven, the material does not get heated because the material does not having about the dipole. The dipole momentum is completely zero. Here in polar dielectrics, it is having for the positive and negative charges do not coincide here. Okay, it is the asymmetrical charge distribution. Polar content example is water, alcohols, quartz, etc. Non-polar content example is CO2, CH4, methane and benzene. Based on the polar and non-polar dielectric, we can easily calculate about the what is the dipole moment, okay, what is the bond length. We can easily calculate about the relaxation time also. We can easily calculate about the volumetric parameters like molar volume, what is this excess permittivity, relaxation time, excess dielectric permittivity, dielectric constant, many parameters are there. Okay, coming to the next slide. What is the physical significance of dielectric material? Especially for dielectric material, we are taking for polar and non-polar material. In this equation, the complex dielectric permittivity as a function of real part and imaginary part. This is the real part and this is the imaginary part. The real part of dielectric permittivity is also called about the dielectric constant, and it is a measure of the amount of energy from external electric field stored in a material. The imaginary part is also called about the dielectric constant. It is the loss of dielectric material. Loss means it is a measure of the amount of energy lost from the external electric field. So the complex dielectric permittivity is equal to the real part and imaginary part. So polar metal having about the loss exists, non-polar metal having the no loss. It is suitable for the liquid dielectric material. In the liquid dielectric material, we can easily identify about the what is the loss factor. Okay, for example, this equation represents about the phase lag between the voltage and current or electric field and rate of polarization. Polarization is equal to the dipole moment divided by volume. Here, real part indicates about the storage of energy. The imaginary part indicates for the dielectric loss. Okay, this equation is suitable for the microwave heating. In the microwave heating, we can easily see about the what is the storage factor and what is the loss factor. So here negative sign represents about the absorption and dissipation of energy into the heat form. Positive sign indicate about the emission in the form of the light. You can see about the optical region, mu is equal to n plus ik. This equation is suitable for the material. In this physical significance of dielectric material, we are calculating about the tan delta. Tan delta is equal to the imaginary part divided by imaginary imaginary part divided by real part. It is also about the loss factor. You can see here tan delta is equal to E double prime divided by E prime. We can write delta is equal to tan inverse of dielectric loss related divided by storage of energy. This tan delta is called loss tangent factor. You can say it is the dissipation factor and also for the loss factor. It is purely related to the complex dielectric permittivity, mainly depends upon the frequency and temperature. If frequency and temperature or frequency. See, for example, importance of dielectric material in capacitor. So capacitor is the energy storage device. You can see about the three different diagram. Parallel plate capacitor with free space between the material. Parallel plate capacitor with free space between the plate. I am taking for one positive charge and one negative charge. The capacitor is there. Voltage is applying electric field direction. For example, a slab of insulating metal is inserted between the plate. There is an external current flow indicating about the charge is stored in the plates. You can see the dielectric material is placed here. What happens? Once the dielectric material is placed here, it stores about the energy. Third diagram, the capacitance has increased due to the insertion between the medium between the plates. The equation is C is equal to epsilon naught R A divided by D. So here the capacitance is directly proportional to the area is the area of cross section. D is the distance between the plate. This permittivity, dielectric constant indicates about the material property. It is said to be storage of energy. A is the area of cross section and C is the diagram. So in this metal, what is the importance of the dielectric material and what is the importance of the capacitor? One is the external current flow from indicating the more charge is stored in the plate. One is the insertion between the plate. It is the area of cross section is increased. Just about the comparison about the capacitor. So what are the dielectric material? What is the dielectric constant? Dielectric constant symbol is this one. This is about the dielectric constant. So I am taking for different materials and different dielectric constant. For example, air, the dielectric constant is 1. Alumina, the dielectric constant is 10. Like different metal, dielectric constant 27, 42, 700. You can see here. Lead, magnesium, neobed, the dielectric constant is 2000. So H2O, for example, if you take for polar content H2O molecule, the dielectric constant is 57. It is the 57. Water content dielectric constant value is 57. So every time we are taking for the H2O only because of it is the polar content material. Okay, this is the example for how the metal with the dielectric constant. So dielectric constant will be very high, 8 to the lead, magnesium, neobed. Less for air, more for the material. So here, based on the different types of dielectric material properties, example, we have to analyze about the what are the fundamental definitions of dielectric material. Especially in dielectric, fundamental definitions is the very important for the to calculate about the polarization and for dielectric constant, relative permittivity, what is the magnetic susceptibility, how to calculate about the polarizability, we can discuss one by one. See here, electric dipole moment, permittivity, electric polarization, polarization vector, electric flux density, and also for electric susceptibility. These are all the important for the dielectric material. We can also see about the what is the relationship between the electric displacement vector, electric field intensity, and dielectric constant. First of all, the fundamental definitions of dielectric dipole is dielectrics are the materials having about the electric dipole moment permanently. In the previous slide only, due to the bound charges, they constitute an electric dipole moment. Based on electric dipole moment, the metal is classified into polar and non-polar metal. So, electric dipole moment is one of the key aspect for dielectric material. So, what is the dipole moment? Dipole is an assembly in which equal positive and negative charges are separated by a small distance. One positive charge, one negative charge separated by small distance, it is said to be dipole. The dipole is placed in electric field, it acts like electric dipole. The dipole is placed in magnetic field, it acts like magnetic dipole. So what is the dipole momentum is, in the dipole moment, polarization is important. Polarization is equal to dipole moment divided by volume. So I am taking the product of magnitude of either of the charges and separated distance between them is said to be dipole moment. So in the dipole moment, the unit is divide. It is for the microscopic quantity. All dielectrics are electric insulators. They are mainly used to show about the electric energy. So polar content material, the storage of energy is very high important. Example: glass, mica, plastic, water, and molecule. Now you can see here dipole. This is for the dipole moment. Mu for induced dipole moment. Q is the charge, dl is the length of the element. The unit of dipole momentum is dipole. So this is the diagram for the how the material is classified into the unpolarized material and polarized material. So here in the polarized material, you are applying for external electric field. We are taking for positive charges on one direction, negative charges on one more direction. So here the charges are accumulated with each other. Unpolarized material, in the absence of external magnetic field, the charges will be oriented in different direction. It is for the accumulated. Induced charges will take place for polarized material. So coming to the definition of relative permittivity, relative permittivity is denoted by ER. This is for relative permittivity, or we can write this one, dielectric permittivity. Okay, so permittivity is equal to Q by Q naught, or we can write capacitance of the charged capacitor, capacitance of the capacitor with air medium, E by E naught or F by F naught. So here dielectric constant or relative permittivity can be defined as the ratio between capacitance with medium to the capacitance or free space, or field between the medium to the field between the vacuum or space. This is for free space region. Okay, that is about the dielectric constant definition, or we can define about the dielectric constant one more definition. Epsilon ER equal to permittivity divided by permittivity of free space, or dielectric permittivity is equal to free space into relative permittivity. These three parameters are dielectric constant only. So dielectric constant is defined as the permittivity of free space into the relative permittivity of the material. So the units is Faraday on Faraday per meter or Coulomb per Newton per meter. So in this category, I am defining about the three notations here: Q by Q naught, C by C naught, E by E naught, F by F naught. If we take for the capacitor, these equations, parallel plate capacitor, we are framing about the different notation. Epsilon R. Epsilon R is relative permittivity. Q is charge on the plates with a dielectric material. If we take for charge of parallel plate capacitor, we are identifying about the Q positive charge, one more capacitor minus. This is negative charge capacitor. Like, okay, this is about the orientation. induced charges are developed. So here Q naught is charge on the plates with free space. Okay, free space between the plates. C is the capacitance with dielectric medium. What is the important? C naught is capacitance of a parallel plate capacitor in free space. E is the electric field medium and E naught is electric field due to the free space. In the previous diagram, we are keeping about the dielectric material and also about the capacitor. That this equation is applicable for in previous diagram. Coming to the next slide, what is the polarization is important in the dielectric material. How we can see about the electric polarization, ionic polarization and orientation polarization. It is the different topic related to the dielectric material. Simple one, polarization is equal to dipole moment divided by volume. We are writing here polarization is equal to dipole moment divided by volume. Based on this definition, consider an atom is placed inside an electric field. Here, the center of positive charge and negative charge are displaced along the field direction. Okay, while the center of negative charge is displaced in the opposite direction. So what happens mean dipole is produced like positive charge, negative charge separated by some amount of distance P equal to Q into D. Dipole is produced. So here when dielectric material is placed inside an electric field, such dipoles are created in all the atoms inside. Here, the process of producing electric dipoles which are oriented along the field direction is called polarization in dielectrics. We are taking here dielectric material, it is placed in electric field. Such dipoles are created in all the atom inside. So, the process of producing electric dipoles which are oriented along the field direction is called polarization in dielectric. Coming to the next slide, what is the dielectric constant and what is the relative permittivity? What is the relationship between the E naught and ER? So, dielectric characteristics are determined by the dielectric constant only. It is defined as the ratio between permittivity of the medium to the permittivity of free space. This is the important relation related to the dielectric material. Relative permittivity is equal to the capacitance of the capacitor with dielectric material divided by capacitance of the capacitor without dielectric material. We have to write the equation related to the permittivity and capacitor. So, ER is equal to E divided by E naught. This is about the free space. E naught means free space. So, dielectric constant has no units. Okay. Coming to the next slide, what is about the polarizability? So, with the help of the polarizability, we can calculate about the ionic polarizability, electronic polarizability and orientation polarizability and also for space charge polarization. Simply, polarizability is denoted by the symbol is alpha. Here, when the strength of the electric field E is increased, you can see the equation. When the strength of the electric field E is increased, the strength of the induced dipole moment mu also increases. It is directly proportional to the intensity of the electric field. So, when the strength of the induced dipole momentum is decreases, when the strength of the electric field is also decreases. It is directly proportional to the intensity of electric field. Therefore, the polarizability in the mathematical notation we can write as mu by E, induced dipole moment per unit electric field. Alpha is polarizability, mu is the induced dipole moment, E is the intensity of the electric field. That's why mu is directly proportional to the E. Alpha is said to be constant of proportionality is called the polarizability. So, how to define the polarizability means alpha is equal to mu by E. That means induced dipole moment per unit electric field. With the help of polarizability, we can calculate about the alpha I, that is for ionic polarizability, alpha E for electronic polarizability, alpha R, alpha naught, that means orientation polarizability, and alpha S for space charge polarizability. Therefore, total polarizability alpha is equal to alpha I plus alpha E plus alpha naught plus alpha S. So, total polarizability is equal to the ionic, electronic, orientation and space charge polarization. In this equation, we can also find out about the induced dipole moment mu is equal to alpha E. So, we have to substitute alpha is equal to four types of polarizabilities: ionic, electronic and orientation and space charge polarization. Compared to this ionic, electronic and orientation polarizability, space charge polarization can be neglected. We can discuss about the uh, next class with the help of the types of polarization. It is the important equation for the dielectric material for the polarizability. So, polarizability means induced dipole moment per unit electric field. Its unit is Faraday meter square. Coming to the next slide, what is the polarization vector? The polarization vector can be defined as dipole moment of the dielectric material is called polarization vector. Dipole momentum is very important for the polarization vector. We are taking here mu is the average dipole moment per molecule and capital N is the number of molecule per unit volume. Then the polarization vector is equal to, I am taking about the total dipole moment divided by number of molecules into the number of molecule divided by volume. Therefore, polarization is equal to the total dipole moment divided by the volume. In the mathematical notation, we can write P is equal to mu into N. Mu is the induced dipole moment, N is the total number of molecule per unit volume of the material. So, the dipole moment per unit volume of the solid is the sum of the individual dipole moments within the volume, and it is said to be polarization of the solid. This is about the one of the fundamental definition for the dielectric material. Coming to the next slide, we can also find out about the electric flux density or electric displacement. It is also for the important definition for the dielectric material. Now you can see here electric flux density or electric displacement at a point in the material is given by D is equal to uh, epsilon into E. That means electric flux density is proportional to the intensity of the electric field. So the permittivity, this notation, the permittivity can be written as in the mathematical equation relative permittivity into the permittivity of free space. These two are the dielectric constant only. Therefore, the relative permittivity is equal to the dielectric permittivity of the medium divided by permittivity of the free space. So permittivity, that means dielectric permittivity or dielectric constant is equal to the relative permittivity into the permittivity of the free space. This is about the equation for the dielectric permittivity or dielectric constant. From the equation 1, E is the electric field strength or ER is equal to relative permittivity, E naught is equal to permittivity of free space. For example, as the polarization method, additional flux density arising from the presence of the material as compared to the free space. It has the same unit as electric displacement. Compared to the equation number 1, electric displacement D is equal to E naught into capital E plus P. This equation is valid for the free space. So, D is equal to permittivity of free space, electric field strength into the relative permittivity. Already we know this equation. Okay, from equation 1, substitute equation 1 in equation 2. Here, substitute D value from the equation 1, we can write E naught into ER into capital electric field strength is equal to free space into electric field strength plus P for polarization. So, therefore, polarization P can be written as free space relative permittivity electric field strength minus E naught into capital V. Take E naught common, that means take the dielectric constant or free space common, we can write this equation as in this way. So, this is the important equation for the polarization vector related to the electric flux density. Compared to the equation 1 and equation 2, this equation tells about the what is the relationship between the P, E and D. Okay. Coming to the next slide, we can also find out about the electric susceptibility. This is the electric susceptibility symbol. We can write psi E in this way. Okay. So, the polarization P is proportional to the total electric flux density and is in the same unit direction of field strength. So, we can write polarization P is directly proportional to electric flux density. Once if you remove the proportionality factor, we can write about the in this way. This is for the electric susceptibility symbol. Since D, the electric displacement vector D is equal to epsilon into E, you can write in this way. So therefore the polarization vector can be written as in this equation we already seen in the previous slide. Substitute about the, we can write this equation electric susceptibility equal to P by epsilon into capital E. Substitute about the polarization equation. In this equation E naught cancel, E cancel, we get electric susceptibility is equal to relative dielectric constant minus 1. This is about the fundamental definition for the electric susceptibility, dielectric constant, electric displacement, what is the flux density, what is the polarizability, what is the relative permittivity. In the next class, we can discuss about the what are the types of polarization related to the polarizability, how to calculate about the ionic polarization, electric polarization, orientation polarization and phase charge polarization, and also find out about the induced dipole momentum of polarization. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.